Welcome everyone. Welcome to our second lecture in earthing system. During our last lecture, we discussed the importance of soil resistivity, and we discussed the type of method to measure the soil resistivity for high voltage earthing purpose, also for low voltage earthing purpose, for any purpose of a design that requires you to obtain an accurate soil data. And all our discussion was based on IEEE standard. Today, we are going to show you how do you obtain or how do you convert the obtained field data into a soil structure suitable for earthing assessment. This will give you a great benefit if you don't have an advanced software, or if you want to have just a quick hand calculation to compare what your designer provided you. This will give you a great tool. And you can put it into Excel if you have a good computer software skills. You can also generate your own code. So during today, we are going to go a little bit about introduction, soil resistivity structure discussions. Now, according to IEEE 80, this is very important, guys, to understand. Interpretation of apparent resistivity obtained in the field is perhaps the most difficult part of the measurement program. You went and you obtained data. You cannot obtain 100% of the data from the field. There will always be some errors because you did not measure every single spot. So how are you going to interpret the interpretation of this data? The base objective is to drive a soil model that's good approximation of the actual soil. No one knows what's underground. That's why it's very important for us to have a good approximation of the actual soil if we are going to design an acceptable or an adequate earthing system. The most commonly used soil resistivity model are the uniform soil model and the two-layer soil model. We're going to discuss about uniform and two layers. Two layers soil models are often a good approximation of many soil structure. That's according to IEEE. So we are going to stick to IEEE standard. It's one of the standards that used worldwide. Interpretation of the soil resistivity measure may be accomplished either manually or by use of computer analysis techniques. During our lecture today, I am going to show you how you can do a hand assessment using IEEE 80 standard. Before we go into the analysis, I would like to explain to you the type of available, or these are 5 types of soil structures. Type A, see, when you have a fixed number, I mean you have one type of soil, one layer, homogeneous soil. Let's say I want to look at B. What does B tells me? Low soil resistivity at the beginning, and then high soil resistivity. So I have 2 layers. The top one is low resistive layers overlaying high soil resistivity. So now I have, this is my ground. I have low soil resistivity, I have high soil resistivity. So I have 2 layers. The top layer, it's a low soil resistivity. The bottom layer, it's a high soil resistivity. Let's look at C. Guys, C shows me that it's a 3 layers. Low, high, and low. So if I look at it, if I want to look at it like I have 3 layers. This layer is high, low, low. When it comes to soil structure. Let's look at D. D, I have this top when you have the top layers, this represent the top layers. Can you see? High over low. I have 2 layers, 2 soil resistivity layers. The top one is high, the bottom one is low soil resistivity. And E, can you see this issue? Can you see this E? How is it going like this? That means I have an issue with my soil. This issue could be contamination, could be any other reason. So I need to check. If I get something like this, I need to go back and check it. Make sure to go and do more investigation around this area to make sure why this happened. As we saw last time, if I have a substation, from my previous lecture, I need to go 300% its size to have an accurate or more accurate data. So if you have a substation, I want to put a substation in here, I will go do multiple tests. Why do I do multiple tests? Remember last time, our previous lecture shows you the winner. How does the winner, you have 4 probes. How does it go? You remember this? Depending on each one of them has a. So you want to make sure that you cover this area. You cover it sideways. You cover this area. You want to be more accurate, you can do another one. But unfortunately, you cannot cover 100%, the entire 300% of your substation size. There will be always room for an error. There will always be room for an error, but definitely, if you do 1 line, it's not sufficient. 2 lines is not sufficient. This is very recommended, because at least if you have the time and the resources, you can do another one. Another test. So, please, avoid doing only 1 test on your site. You have to do multiple tests to make sure that it captures the entire soil area. And you have to go 300% of your size if possible. More information, refer to our previous video. Now, that's a test we performed. We used to use this test to educate engineers as an example. So you have 4 wires, 2 will go this way, 2 will go this way, and then you will measure using an accredited device to obtain the data. How else I'm going to obtain the data? I need to go ahead and measure. If this is my area, I do 1, 2, I do 1, I can do 2, I can do 3. So I need to make sure that I captures everything. That I capture all this information. By the way, this was done in Western Sydney University, a part of an education workshop with Engineers Australia. Now, you obtain the data. We said we separate A for every single A using winner method. I obtain the data, I record the data. After I record the data, I collect, let's say, 50 measurements, 20 measurements, 30 measurements. I need to go now. What do I do with all these measurements? I need to find a soil structure that I can use for my design. Look, this is very important. A uniform soil structure should only be used if the variation in the measurement apparent resistivity is low. What does this mean? For example, let's say I have A, I have rho. Let's say A is 0.5, for example, 1, 2, 4, 6, 8. This is in meters. Let's say this is now, for example, 60. This is ohm per meter. Let's say that's at 65, 70, 68. Maybe now you get, like, for example, 55. You go back at 65. So the variation is very small. You can vary more. Maybe in here I will go another one. Let's say in here I have, for example, 300. Then in here, for example, I have at 1 meters, I have 250. Suddenly, when I go to this one, I have 100, 70, 65, 85. There's a big difference. Now, I can eliminate this if I want and focus on this one. Therefore, I can drive my earthing system on the lower module, but this will be done during our next video. So if you have a small variation, I think in my personal view, 10% should be acceptable. In some cases, 20% is acceptable when it comes to variation. But when you have 300% variations, you shouldn't. Because if you add this to this will make it dominant, and this is the top layers. So you have to be very careful. A uniform soil structure should only be used if the variation in the measured apparent resistance is very low. Your machine, every time you press the machine for winner, will give you the apparent resistance. I hope that's clear, guys. So it's very important. This have a rare occurrence in practice, especially in a developed area. During my experience in this field, one of the biggest challenges whenever I receive a report to review or to do audit on, they use uniform. And when I check on the data obtained, there's a huge variation, which means you have a very high error. If a large variation occurs, the uniform soil is unlikely to yield accurate result. According to IEEE standard, its more accurate representation of the actual soil condition can be obtained by use of 2 layers soil module. So as a project manager from any discipline, computers, electrical, civil, mechanical, management, doesn't have to be an electrical engineer project manager. After you see this lecture, all you have to do now is pick up your earthing report. Make sure they provide you with the table of the field test. If there is a major variation in the result and they used uniform, tell them that's against IEEE recommendation. Please change it. Please change it. Now, if the changes is very small, you can use this equation. So this is the measured resistivity, soil resistivity. This is Ni, is the number of measured points. This only happened under the condition. Only happen under the condition where there is a small variation in these values. Now, another approach to determine the uniform is by using the maximum plus the minimum and you divide it by 2. So this is another approach to use the uniform. However, this equation, it's not recommended the use of this equation for a ground grid without ground rod. What does it mean without ground rod? Some people use only mesh. If you don't have a ground rod down, it is not recommended to use this equation. You must have a ground rod to use this equation. Under the condition, there's small variation in the measured resistance. If the below equation is employed to design the earth grid, the ground rod should at least reach the depth of the lower. If you remember from Wena, this will go down. If this is A, this in theory goes A. That's in theory. If you remember, that's what we discussed during last video. So you should make sure that you have a deep electrode to reach at least where maximum and minimum. You chose these two elements. You should know roughly at what depth these two are measured. And you should make sure that you have an electrode that goes down to this layer of soil. Now, so to use this equation, I have 3 conditions. Condition number 1 is small variation in apparent soil resistivity measure. Number 2, yes, your earthing system must have an electrode. Number 3, condition number 3, the electrode must reach the lower resistance. So if this measured, for example, this measured at 10 meters or 5 meters, you need your electrode to reach this area for this to be effective. Now, uniform soil structure. During our research, we found that there is a lot of approach. There are several methods suggested by different authors to approximate a non-uniform soil with uniform soil model. Hold on a second. What we just discussed before is it's a uniform soil with a small variation. So if you remember when we sketched A, so now this will be like this maybe. Okay, it's a small variation. So when you get the average, you get like this. Now, if you have non-uniform, if you have a non-uniform, for example, if you have it like this, how would I get a uniform soil? I get rho to represent all this. What I'm going to show you is based on published research. Previous works published under this research addresses when the approximation of non-uniform with uniform soil model yield accurate result. This journal is available online, which is being published. You guys can access it and you can have all the rationale behind it. That was published in 2013. Now, what does this tell us? You guys have stuff called negative reflection coefficient and you have positive reflection coefficient. Go back to these publications for more information. But what I can do is, if I have 2 soil layers, by introducing the apparent soil for everyone, that will make my life easier because then I can go ahead and use my equation for the earth grid resistance, for your step and touch, for your transfer voltages. So now I can use this equation when I have a negative reflection coefficient for the K, and when I have a positive reflection coefficient for the K. I have this, that. This if you have two soil layers. H is the separation between them. Guys, please keep in mind, this data, it's very important when it comes to the third lecture, third video, where we are going to learn how to calculate or estimate the resistance value of your earth grid. Two-layer soil structure. That's where the important part. Because to find the apparent of a non-uniform system, I need to find rho 1, rho 2, and the H, the separation between. Determine the total layer using hand calculation. You want to use Sunday's chart or a computer software. Like we spoke today, we are going to rely on hand calculations. Sunday chart. This is based on IEEE 80. What do I need to do? All these steps. We are going to go step by step, show you how to use step by step to achieve your desired outcome. Let's go ahead. Step 1. So without going through it like this, we will break it into 1, 2, 3, 4 until reach each one. Step number 1, I need to obtain the data. I use Wenner method. I used a Wenner method. For every spacing, I measured. This is in ohm per meters. This is separation in meters. I go into Excel file. I sketch this. I sketch it. Based on what I can see now, I have low soil resistivity over high soil resistivity. So as you can see, I already have two layers. Now I need to distinguish, I need to find top layers, rho 1, I need to find rho 2, and I need to find H. The depth of the first layer. So I have, this is rho 1, this is the depth of H of rho 1, and that's the soil resistivity 2. First of all, I get this figure to tell me, hold on a second, that's represent two layers. Great. Step 2. I need to estimate this resistance and this resistance. Resistivity. So what do you reckon this one's going to be? 4, 5, 6. It's going to be somewhere in here if you want to be more pedantic about. This is 1, 2, 3, 4. So if you want to look at it at the first couple of meters, it's going to be somewhere around here. It's going to be somewhere around here. I want to measure the top layers, which is about a couple of meters. As you can see, that's a small system. It only goes up to small system. So I'm designing a small system so that electrode shouldn't, the system shouldn't go too deep unless I have a very high soil resistivity. But I can see the soil resistivity is very low. Now, so I have 4, 5, and 6. It's about 5. Your soil resistivity at this point. What about this point? This point, the rule of this point is I need to continue this until get almost, and I estimated this. This is our energy. I estimated it to be 20. Because I need to continue. I couldn't. The area didn't allow me to go to the infinite. In reality, this one, I keep going down like this until it's sufficient, because this one shows that maybe it's going to go up to 20. Because this one in reality is going to go like this. Keep going. I estimate it to be a 20 ohm per meter. Step number 3. Compute the value. Rho 1 over rho 2 or rho 2 over rho 1. What do I have? 20 over 5. It's equal 4. This then select on the curve. Where is the 4? Where is the 4? This is row 2 over row 1, if you remember from Sunday graph. Where is the 4? This is row 2 over row 1. I found it to be 4. 20 over 5. This reflects to what I found, the 20 over 5, 4. So I sketch it a little bit like this. If I put this into a software, of course, it's going to give me more accurate one. I sketch it like this. So now I sketch this one. Then I need to select row A over row 1. That will tells me where's the 4? A over H. Where is it? Is that clear, guys? Is that clear, guys? This is crossing this one. It's not crossing this one. If this goes like this, if this goes like that, I'll get cross with this one. I need to see where's this. Don't worry about this. Is row 2 over row 1. So when I get this cross, I put this 2. Then I need to go to the next step. Remember now, step number 5. Step number 5 is where it crosses this line. This is row A over row 1. I will put it and I put a line like this. Then I found this to be 2 from the graph. Step number 6. Look, what do I find from this? 4. So from this figure, when that crosses, this is give me 2, this give me 4. Now, compute row A using row A over row from step 5. So therefore, I have row A is 10 ohm per meter. So after what we've done is, we obtain row A is 10. I go back and check where does this intersect with my measurements. I found A. Remember, this is A. And then, after I intercept with this one, I go back. I have A over H is equal 4. From the Sunday graph, I can find now H is 2.075. And then I can finalize my table. Let's go do another example. So let's do another example. By doing another example, let's go back to the original one, the original Sunday graph. Went too far. So let's look at another example, guys. Let's look at, that's my A spacing in meters. That's my ohm per meters. Let's assume I have another one like this. This one, I wanted to say, let's say 100 ohm per meters. This one, I keep taking it down all the way down. By the way, I should keep measuring until I start getting some sort of lead, and then I goes back. Let's say that's to be 20, or let's assume 30 ohm per meters. I sketch this one. Then I calculate rho 2 over rho 1. Will give me 30 divided by 100, 0.3. If you put it 20, by the way, guys, look, if you put it 20, 30, 0.3. Where does it 0.3 is going to sit? 0.5, 0.2, 0.1, let's say somewhere around here. So I sketch this, or like this. You sketch it properly. You can use software. So now, where did it cross? It crosses in here. So I have rho A over rho 1, it's equal to 0.5. So rho A is equal to 0.5 times 100 will give you 50 ohm per meters. Can you see this 50 ohm per meters? So now, what do I have to do? Step number 2 is 50 ohm per meters. I go back and I say, where's the 50? Let's say that's a 50 ohm per meters. Let's assume that's 40 meters. For example, I go back into here. Where does this located? 2, 3, 4, 5. So maybe it's about 2.5. If this is 2, this is 5. Let's say this is the 3, 4, and 5. So it's at 2.5. It's at 2.5. So if it's 2.5, that means I have A over H, it's equal to 2.5. So H, it's equal A divided by 2.5. 40 divided by 2.5. That's what will be H. So now I have two soil resistivity. The top one is 100, the bottom one is 30 ohm per meters, and the H is 40 over 5, over 2.5. Is that clear? That's how I managed to do all my system. With a lot of experience in the future, with a lot of experience, I pick up the data from the field and I look at it. This is the shape. Look, it's going to be about 100 and let's say 30. It's about 20 meters, 30 meters, depending on this. If this is going sharp like that, or is it going light? You'll be able to straight away, it's going to be high, H is going to be large, or H is going to be small. I hope that's clear, guys. It's a very simple task. It's a very simple task. With the practice, it will become very easy for you to assess and to determine. Is that clear? During our next lecture, we are going to capture how to use this data, how to use the soil system, soil structure that we obtained to compute the soil resistivity, the actual resistance of the earth grid embedded into our soil resistivity, how to calculate the step and touch, actual step and actual touch, not the allowable limit, the actual one, which is going to be based on heavily impacted by our calculation of the soil structure. I hope that was beneficial for you. Until our next lecture, I hope you stay safe and I'll see you next time.